Let E be a given set, then the following statements are equivalent. First one is A is a measurable. Second, given epsilon is greater than, there exists a open set O contains E such that outer measure of small bracket starts O minus E is less than epsilon. Third, there is a G delta set. G contains E that outer measure of small bracket starts G minus E bracket close is equal to 0. Fourth, given epsilon is greater than 0, there is a closed set F contains C such that outer measure of bracket starts C minus F less than epsilon. And fifth, there is a F sigma set such that F is a subset of E such that outer measure small bracket starts E minus F bracket close is equal to 0. Now first employs 2. First way is here that E is measurable, then this gives the resultant, this particular resultant. Supposing M outer measure of E is less than infinity, then there by theorem let E be any set, then given epsilon greater than 0, there is open set O contains E such that outer measure of O less than equal to outer measure of E plus epsilon. There is a open set O contains E such that outer measure is less than O less than of outer measure of E plus epsilon, such that both the sets O and E are measurable. So outer measure of O minus E is equal to outer measure of O minus outer measure of minus a outer measure O minus outer measure E is less than epsilon. Now considering the case when outer measure of E is equal to infinity, writing the R as the set of all the real numbers as a union of disjoint finite intervals, that is R is equal to union of In. Thus if En is equal to En intersection In for measure of En is less than infinity, we can thus find that open sets O n contains En such that outer measure of small bracket starts On minus En less than epsilon upon 2n. We define O as union of n varies from 1 to infinity On. Clearly O is an open set. O contains E satisfies that O minus E is equal to union of n varies from 1 to infinity On is equal to n varies from 1 to infinity On. C is a subset of union of n varies from 1 to infinity small bracket starts On minus En is less than epsilon. Hence outer measure of O minus E is less than sigma n varies from 1 to infinity outer measure of On minus En less than epsilon. So which implies that is outer measure of small bracket starts O minus E bracket close is less than epsilon. 2 implies 3. The given epsilon is 1 upon n, there is a open set On contains E with a outer measure of On minus E is less than 1 upon n. We defines G is equal to n varies from 1 to infinity On. G is a G delta set such that G contains E and outer measure of G minus E is less than equal to outer measure of On minus E is less than 1 upon n for all values of small n belongs to n and tends to infinity, which proves the part third. Now 3 employs first, writing that E is equal to G minus E, but since the set G and G minus E are measurable, since G is a Borel set and G minus E is a outer measure of 0, hence F is a measurable. 1 implies 4. Since E complement is measurable, so in a view of second, there is a open set O contains E complement such that outer measure of small bracket starts O minus E complement is bracket close is less than epsilon. but O minus E in complement is equal to O minus E complement. Taking F is equal to O complement, and assertion V follows that since F is equal to O complement, so fifth result will now fourth gives to fifth result. The given En is equal to 1 and there is a open set E with the outer measure of E minus Fn is equal to 1 and we define F is equal to union of Fn. There F is a F sigma sets such that F is a subset of N, so F is equal to E and M is AFEN 1 for all values of N. Letting N tends to infinity, then the result follows. So V employs first, fifth result employs first. The proof is similar to that. The third result is